Good afternoon, everyone. I am Neeraj Dhariwal, presenting on the topic room temperature ethanol sensor based on novel zinc ferrite nanoparticle cross-linked with the hydrogel. And I'm doing PhD under the supervision of Dr. Vinod Kumar from Netaji Subhash University of Technology. So in my presentation, I will be covering the topics literature survey, introduction, methodology, results and discussion, application, and finally we will going to conclude this. So introducing my presentation, I have prepared zinc ferrite cross-link gel. This is the novelty, one of the novelty that none of the paper has presented or synthesized gel based on any kind of ferrites without the use of basically the polymers. So we haven't used any polymers in this synthesis. So our prepared gel shows exceptional ethanol selectivity and the sensitivity. And the sensor has a good response time of 15 seconds and a recovery of 13 seconds at room temperature, which is quite fast. And this sensor is used for the real-time ethanol vapor monitoring, for including the food and beverages, automotive companies, and breath analysis as well. We will be discussing in the results section. So coming to the novelty part, this gel-based zinc ferrite synthesis has been done, which is the novel. Also the low-cost simplicity, flexibility of the sensor, and the tunable sensitivity with faster response and recovery time. So coming to the methodology part, we will be discussing about the synthesis of this ZnFe2O4 gel. We took zinc nitrate and iron nitrate, combined both of these after stirring of around 30 minutes at 500 RPM. Then after mixing that, we used a large amount of oleic acid because we didn't use any kind of say polymer. So oleic acid was used just to attach these kind of particles with each other. We will be seeing in the FSM in the further slides, and a small amount of NaOH just to start the precipitation, or can say the crystallization. Then put it into the hydrothermal, and then finally we got the zinc ferrite gel as seen in here. So we will discuss ethanol sensing setup a bit later. Firstly, we will do is we will synthesize a sensor fabrication. We'll fabricate a sensor. These are the IDs. These are just flexible IDs we used. We mixed the gel, a kind of slurry we made, and then deposited over these IDs and put it into the this vacuum oven for around 2 hours at 100 degrees Celsius, just to deposit or to get a good adhesion. This is a sensor dimension we used. So the film thickness we measured was around 10 micrometers. So coming back to the ethanol sensing setup, after the fabrication of the sensor, we used this for the gas sensing. We have a gas sensing chamber over here attached to the gas, that is ethanol we used, and an air to just to evacuate or to normalize the atmosphere. We connected this chamber with this ID interdigitated electrode with the source meter, for which we took the reading in the source meter and then connected it to the PC. That is an optional. We can connect the PC, or we can directly take it from the source meter as well. Then coming to the results and discussion part, this is first one is the XRD of ZnFe2O4. It shows a broad peak, that is small size of crystalline domain, which demonstrate that the crystallization has started but not completed as yet, and which is confirmed from the FSM image. This FSM image shows we can see this blurrish part, which shows a gel kind of structure. I have zoomed this one. This part shows these are the nanoparticles which are attached with the gel as well. So these nanoparticles, due to the small amount of NaOH and small time of putting into the hydrothermal, so this shows a flower-like structure which increases the porosity and can say the surface to volume ratio, which is the primary concern of any kind of gas sensor. This shows the EDEX spectra of zinc ferrite. Now coming to the ethanol sensing mechanism, this image shows the depletion region in the presence of air and in the presence of ethanol atmosphere. So initially, when it comes into the contact of air, the electron will be absorbed onto the oxygen and will increase the depletion region, which further increase the resistance. And while in case of ethanol, when we insert into the ethanol atmosphere, the electron is transferred to the material, which obviously will decrease the resistance and obviously the depletion regions, for which we get a kind of decrease in resistance and increasing current. So we'll get the response. These equations shows the similar things which I have said. This is another the results we got. First one, the part A shows the repeatability curve. As the resistance of the sensor was of around 2 into 10 power 6, that is 2 mega ohm nearly. When we insert it into the ethanol atmosphere, it suddenly shows a dip into the resistance. Here we can see in the presence of gas, we can get a dip into the resistance, which shows the response in the presence of ethanol. And when when the gas is evacuated using the pump, it again gained the same resistance of 2 mega ohm nearly, and the same curves are repeated throughout the experiment. Then another graph, this graph B, shows the variation with the ppm. We got the minimum of 1 ppm. Then with the bending, like we bent the device we had with the sensor we fabricated, we bent and we got variation at different ppm. This shows the response and recovery slide. This one is one of the novel work we have done. There is variation in the sensor response at lower temperature, like we can do at the room temperature around 25 degrees Celsius, 10 degrees Celsius. But what about at minus temperatures? So we got the results at minus 38 degrees Celsius. Obviously, the result at room temperature was higher, but we get around variation of around 2 to 3 times at minus 30 degrees Celsius as well. So which is due to the novelty in the, I can say, material dimension, or we can say the gel part, which is basically formed with the humid atmosphere as well. So another last graph shows the LOD, limit of detection, which we got around 0.2 ppb. Pardon, 20 ppb we get from this one. So for this, the 20 ppb is quite low detection limit. This graph also shows the variation in the presence of ethanol atmosphere. We can see in situ FTIR over here, which tells when the sensor is came into the contact of ethanol, the bond changes and we get breakdown in different bonds, which is also confirmed by the gas chromatography mass spectroscopy. This above graph shows the formation of acetaldehyde. That is, the peaks we got for that is 44 M by Z and 29 M by Z, which confirms the formation that we saw in the this mechanism, that after the conversion of ethanol coming into the contact of the sensor, it converted into the acetaldehyde, which is also confirmed by the GCMS spectra and the in situ as well, in situ of air as well. So coming to the application part, as the main objective of our research is coming to the application or fabrication of device. So the application source was confirmed by the Delhi Traffic Police. We had a collaboration with them. So we got a slight uh, alcohol content, person drunk with a slight alcohol content and a heavily drunk content. So we got different readings. These are the device was connected through the IoT, and we get the real-time monitoring of that. So this green indicator shows that the person is drunk with a lower limit, which is harmful for the person, and which is also confirmed. The reading was also confirmed by the source meter as well, which was connected through it. These are the application of this ethanol sensor. So the breath analysis, automotive industry, environmental monitoring, food and beverage, agriculture, and medical, as I discussed in the introduction part. So, and what our device gives to it is cost effectivities, fast response recovery, ease of fabrication, high response, and excellent selectivity, which is the major concern, as Professor Misra said in his slides. So developed devices, we have developed the device as well. First one is the basic structure to just know whether it is giving the results or not. And another one is connected with the IoT and Arduino sensor. This is a video which I guess is not able to play here. I will just demonstrate here. It will just take 2 minutes. So this shows, I'll forward it. Here it is, our device, and we have two beakers. First one is humidity, so that the sensor doesn't respond in the presence of humidity. So we have a high humidity over here, and which shows when we inserted our device into this, the LED doesn't glow, which shows the decrease, the resistance remains the constant in the presence of high humidity. While when we inserted it into the atmosphere of ethanol, then we will get a response, as we will be able to see here. So this shows the glow in the LED, which means the resistance has been decreased when it comes into the contact of ethanol. So this was about the device. Now, coming to the conclusion, so we have developed the ethanol sensor based on zinc ferrite gel. It has a high response of around 29. R naught by Rg is 29 at 25 degrees Celsius for 50 ppm. High response and recovery time, and higher durability, stability of the sensor, which can be further used for the different type of application as well. So these are the references I took, and that's all from my side.
Good afternoon, one and all being present here. And this is Dr. Neeraj Kumari, Assistant Professor from K.R. Mangalam University. And first of all, I would like to say thanks to the organizing team of this conference to provide me this opportunity so that I could present my work on this platform. So the topic of my presentation is the novel approach for the synthesis of nanopigments and their applications in the polymer matrix. So if I tell that what is nanopigment here, so just yeah. So nanopigments, we can say that these are the class of the nanocomposite which can show the advantages of both organic dyes and the inorganic pigments. And when these nanopigments can be used as colorant to modify the color of the synthesized product, and also they can improve the various physicochemical properties like their mechanical properties, their thermal stability, their hardness, all these. So generally nanopigments, they are of two types, metal oxide nanopigments and the clay based nanopigments. So here we are going to discuss about the clay based nanopigments. So basically the clay based nanopigments, we can say these are the hybrid material which can be formed by the combination of the organic dyes and the layered silicate minerals. And when these nanopigments are used as colorant in various industries like paint and concrete industry for the optoelectronic applications, printing ink, and they can also be used in the polymer matrix to form the beautifully colored, homogeneously dispersed that polymer films. And these nanopigments, when used as inorganic filler in the polymer matrix, they can increase the color fastness, mechanical strength, as well as the thermal stability of the polymer films. So as we are discussing about the clay-based nanopigment, so let us discuss first of all about the clay minerals. There are two basic units in the clay mineral. First one is the octahedral layer, and second one is the tetrahedral layer, as you can see here. And depending on this tetrahedral and octahedral layer, the clay minerals categorized into the different categories like 1:1 ratio, 2:1 ratio, 2:1:1 ratio. In 1:1, that one octahedral and one tetrahedral layer is present, and is 2:1 group of clay minerals. One that octahedral layer is just sandwiched between the two tetrahedral layer. Just a second, sir. Yeah. So again, this 2:1 group of clay mineral categorized into the different category here, that is pyrophyllite, smectite, vermiculite, elite, chlorite, and mixed layer, and many more. So today in this presentation, we are going to discuss about the smectite and the vermiculite type of the clay mineral. And in these type of the clay minerals, we can see here that these are the basic unit. We can say that where one octahedral layer is sandwiched between two tetrahedral layer, and this space, this is known as the interlayer space, where water molecule and the inorganic ions that could be present. Inorganic ions means you can say like calcium to positive, sodium positive, and magnesium to positive. All these ions could be present. So because of the isomorphic substitution in the clay minerals, the surface of the clay minerals, they are found to be negatively charged. And because of this isomorphic substitution, we can say that clay are the hydrophilic in nature. And here we are also talking that these clay minerals can be used as the adsorbent, or can be adsorbent yeah, and after that they can again this can be used as the nanopigments, right? So because the polymer which we are going to use here, that is the hydrophobic, and the clay minerals, they are the hydrophilic, so this is necessary to modify the surface of the clay minerals, and that can be modified through the ion exchange method using the cationic surfactant that is known as the cetyl pyridinium chloride here. So when this cetyl pyridinium chloride interact with the pristine clay minerals, then there are the possible interaction. First of all, you can see that this CPC is arranged in between the interlayer in form of the monolayer, and means these CPC intercalated into the interlayer by replacing the inorganic ions first of all, and in form of the monolayers, this could be arranged like this. Second arrangement can be this, that in these interlayers that could be present in form of the bilayer, and as I told that the surface of the clay minerals, they are negatively charged, so there is possible electrostatic force of attraction between these positively charged CPC and the negatively charged clay minerals in form of the monolayer and the double layer. So the possibility of formation of monolayer and bilayer, that we can say depending on the concentration of the CPC, that how much amount of the CPC we are using during the modifications. So, first of all, that these pristine as well as the modified clay minerals that can be used as adsorbent for the removal of dyes, that is indigo carmine and the crystal violet. Two type of the dyes we used here. Indigo carmine, that is negatively charged dye, and crystal violet, that is the positively charged dye. So why this is necessary that we are using these dyes? Because when these dyes are present in the water, because of their bright color, we can say, or when the concentration of these dyes is more than 1 ppm, then they are highly visible, which is and because of their non-biodegradable nature, they are recalcitrant, we can say here, and which are harmful for sorry, which are harmful for the aquatic life. So there are different methods that can be used for the removal of the dyes, and here we are using the physicochemical method. And in physicochemical method, one of the most approachable method is the adsorption, where the dye molecule adsorb on the surface of the adsorbent. Now these dyes are removed. Yeah. So before using the batch extraction studies, first of all, we should know that these dyes are pH stable or not. And we can see here that crystal violet dye, which is not found to be pH stable because there is large change in the absorption value, and this absorption value can be found by using the UV visible spectrophotometer. And while in case of the indigo carmine dye, we can see here that this dye is the pH stable. Now, through the batch extraction study, the adsorption behavior of these dyes, adsorption behavior of the different type of the clay minerals was investigated as a function of pH, contact time, and the concentration. And this is the formula which we used to calculate the amount of the dye adsorb. And after applying these batch extraction studies, what we found here, that in case of the crystal violet dye, the maximum interaction was found with the pristine clay mineral. Here we can see here pristine montmorillonite, and this is known as the pristine bentonite, because of the electrostatic interaction. So here there are two type of the possible interaction. First one, which we will discuss in the coming slides. And in case of the organoclay, as the charge of the clay minerals that can become positive because of the presence of the CPC in form of the bilayer. So because dye is that is cationic in nature, and organoclay that is also cationic in nature, so there is possible we can say instead of electrostatic interaction, there is a repulsion between dye and the organoclay, and because of this the amount of the dye adsorb is found to be less in case of the organoclay, as we can see here, as compared to the pristine clay minerals. This is the batch extraction studies of the indigo carmine dye, and this is found just opposite to the crystal violet dye, because indigo carmine dye, that is the anionic in nature, and organoclay, that is the positively charged. So again, there between the organoclay, that is organomontmorillonite, organobentonite, and organovermiclite, the possible interaction that we can say here, that is because of the electrostatic interaction between these two. And same the pristine clay in case of the pristine clay minerals, the adsorption of the dyes that is found to be less. We can see here for only 14.6 milligram of the dye adsorb. Again, same region that dye is anionic in nature and clay is also anionic in nature, so there is repulsion between the dye and clay minerals. So this is the possible interaction in case of the crystal violet dye, that the crystal violet dye that can be present in form of that is in the interlayer of the clay minerals, and also this is present on the surface of the clay minerals, which is only possible through the electrostatic interaction. And secondly, if I told about the maximum possible interaction of the indigo carmine dye with the organoclay, so this is the structure of the CPC and this is the structure of the indigo carmine. So possible interaction is found between this positively charge of the CPC head of the CPC and sulfide group that which is negatively charged in case of the indigo carmine, and possible interaction will be found like this. So we can say that maximum interaction will take place on the surface of the organoclay. So in maximum papers, what we found here that by using a suitable adsorbent, the dyes are removed from the water bodies, but and in these paper only adsorption and resorption processes that can be explained explained. But in my work, what we are trying to do that we are using these dye adsorbent as a pigment to form and that nanopigments are used as colorant to form the colored polymer film. So we are not generating here second generation waste product. Why I am saying this is second generation waste product? Because on one side we are removing the dye from the water bodies, and on second side, if we are not using this dye adsorbent, so obviously.
Can you conclude?
Hello.
Can you conclude, ma'am?
Yes, sir. Give me only 2 minutes. So these can be used in the polymer matrix as the nanopigment, and these clay-based nanopigments, they can be synthesized through the ion exchange methods like this. And these nanopigments, you can see here that what we obtained here, this is the nanopigment of crystal violet dye, and this is the indigo carmine dye. And these nanopigments dispersed into the polymer matrix through the solvent casting method, which we used here. And these are the polymer composite films. So what we found here that in case of the pristine clay minerals, we can easily see the particles in the polymer film, but in case of the organoclay, no particles can be seen with the naked eye. So what we conclude here that the films which are prepared using the organoclay based nanopigments, they are more homogeneous, beautifully colored. And when we compare this color intensity of polymer films with the pure dye, so what we found that if we are using 1% dye to form the colored polymer films, so in comparison to dye, we are using only 0.035% that nanopigments. So this is the light fastness study, and based on the value of del E means this is the color difference between the sample and the reference, and lesser the value of del E, we can say here that more stability of that polymer film is found against the UV visible rays. So you can see here that del E value, that is 12.25 in case of the organoclay based nanopigment. So these polymer films are found to be more more stable against the UV light, and you can see here the difference. So this is my conclusion that polymer film which are formed by the dispersion of the organoclay based nanopigments, they are more transparent, homogeneously, beautifully colored as compared to the pristine clay minerals based nanopigments as well as the pure dye. And polymer films containing nanopigments are found to be more UV stable as compared to the PMA polymer containing pure dye. So thank you so much for your patience. These are my 2 awards which I have got during the conferences, and these are my publications. So thanks.
Sir, good evening to all, and thanks for to give me this opportunity to presentation of my talks on these bugs in today's. That's my title of my research paper. In today's high frequency environments, heterostructures, 2D MOS2 ferrites nanocomposites serve as exceptional microwave absorber materials. And this is my name, Neetu Kumar, and this is my professor's name, Professor Vijay Kumar Kumar, and this is my center, Special Center for Nanoscience from JNU, New Delhi, India. And We next. This is my outline. I complete within
Next.
1 second. This is my outline. First is abstract and second is introductions, and
Oh,
after
next. You move next. Sir.
thank you, sir. Thank you. And this is my abstract. And my abstract is that works is microwave absorbing.
Need
And
to.
yeah,
Next.
yes, next.
No need to show the introduction. We
Oh,
are aware of all these things. Just show your results and
Oh.
conclusion. Simple.
Oh, oh. Sir, this is just like introduction about aims
No,
microwave.
we know about.
Oh.
We know
Thank you,
everything
sir.
about this topic.
Thank you, sir. Thank you,
Just
sir.
show your results, what you done,
Sir,
and
sir,
conclusion.
this is a methodology.
Yeah, you
Of
can
this
work
one.
on it.
Oh,
So
thank
be
you
fast.
so much. Yeah, thank you, sir. Sir, this is a synthesis methodology by hydrothermal techniques, and this is a microwave absorption properties measurements by NRW algorithms in VNA in electronics vector network analyzer. That is a frequency giver, and that is some equations for epsilon and mu for permittivity and permeability, and this is the next equation for Z impedance, and this is a reflection loss equation 20 log Z in minus k Z naught upon Z in plus k Z naught, that is a reflection loss score, and this is a transmission lines methods or using NRW algorithm, and this is a second method for reflection loss method. This is RL is equal minus k 20 log S111. This is a direct measurement to reflection loss, and this is our model to working on microwave absorption material. This is a material in the black color, and this is a metal backing plates to sort out this, and there are incident microwaves to interact the material, and after that some very less amounts of reflector microwaves because of these materials all microwaves to be absorbed, and this is a phenomena is called microwave absorption. And next, this is my synthesis routes, and first of all steering to MOS2 plus Fe3O4 nanoparticles. This is a ferrite nanoparticles, and after that this is a autoclave in 100 ml Teflon lined stainless steel autoclave, and after that to maintain 200 degrees centigrade for 10 hours, and after that centrifuge to at 6000 rpm for 5 minutes and with ethanol and DI, and after that transfer into PPT to Petri plate, and after that drying at 60 degrees centigrade for overnight, and after that we get a MSF, that is my short name of this material, MOS2 based ferrite microwave absorber, that is a MS. Next, this is my results. Results is XRD of this Fe3O4 nanoparticles like ferrite, and this is a XRD of MOS2, and this is a Raman of my MOS2 beer, and this is a relative permittivity. And this is a relative permeability, and this is the same images of MS2, and this is the same image of Fe3O4, it means ferrite, and this is a same image of MSF, yani ki absorber. This is absorber of their composite materials in which MS2 and ferrites, and this is a reflection loss graph that represents the very high reflection loss near about 32.32 decibels at 26 gigahertz, and that is achieving by 1 mm 1.5 mm thickness sample. This is a very challenging to in this field. And conclusion, there are we use the Ka band, that's frequency, and there is a magnetic and agriculture based microwave absorbers also, and MSF as a microwave absorbing sample is synthesized very easily hydrothermal method, and MSF performed sustainable microwave which very high frequency mmwaves is called, that is also called 5G technology also. There are in introduction slides, and MSF present a very challenging achievements of reflection loss minus 32.83 decibel at 26.07 gigahertz within only 1.5 mm thick sample. This it means 99.999% microwave absorption here. And additionally, this can be employed in the creation of cost-effective and light-weight anechoic chambers and substrate for steel technology applications, such as coating materials for defense equipments like fighter aircraft, submarines, and in textile industry as anti-radiation cloths. And this is my reference is starting of first two papers already published in this field. and first is Ceramic International. This is a Springer also. And next, this is my financially supported by, this is my a project by DSTMT. And this is my working support by a Special Center for Nanoscience, JNU. And this is my contact. And I want to, this is my aims for further study, for further work. I want to use to microwave observers in anti-radiation clothes because of high anti-radiation to harm our bodies, our lifestyle. For the purpose of anti-radiation clothes for pregnancy lady and the child and babs and anybody to human lives. And in the defense also, like as a material coated on steel technology, for the purpose of how to divert radar system, how to confuse the radar, and that is a soldier uniform also, and that is
Actually, we are mainly utilizing metal electrodes as the electrode materials in battery, fuel cell, supercapacitors and all. As we all know, metal electrodes are quite expensive, so that it cannot be accommodated for a long period of time. So we have to switch our concept into a more greener or a more compatible method which can store or which can act as electrode materials to store our renewable energy in these devices like batteries, supercapacitors, etc. One such material is MagSeams. MagSeams is considered as one of the wonder materials of the present generation. The development of MagSeam was actually carried out very recently, that is during the period of 2010 to 2011 by a group of scientists in Drexel University. MagSeams are a class of transition metal carbides, nitrides and carbonitrides, which can be generally represented by the formula Mn+1xn, where M represents the kind of transition metals. Most probably it will be a transition metal of group 3D and 4D like scandium, titanium, zirconium, etc. And actually X represents either carbon, nitrogen or a mixture of carbon and nitrogen. So there are several kinds of MagSeams like mono transition metal MagSeams, double transition metal MagSeams, solid solution MagSeams and all. This is a very brief timeline which actually shows the story of the development of MagSeam. It actually includes a period of 2011 to 2017. After 2017 also, there are several research that has been carried out in the field of MagSeam to develop novel materials based on MagSeams. The MagSeams can be generally synthesized from their parent compounds, which are called the Max phases, which are generally represented as Mn+1AXN. As I said earlier, M is any kind of transition metal, X is carbon, nitrogen, or a mixture of both, and A represents an element from the group 13 or 14, like aluminium, silicon, etc. So the synthesis of MagSeams from their parent Max phases is actually carried out using a method which is called wet chemical etching method. A suitable etchant like hydrofluoric acid is being utilized for the purpose. The synthesis of MagSeams from their corresponding Max phases produces surface functionalities like oxygen, F, OH, etc. on the surface of MagSeam, which can be generally represented as TX. So the more convenient method to represent a MagSeam is Mn+1xn-TX. There are several kinds of atomic structures of MagSeams like M2X, M3X2, M4X3, etc. This is a symbolic representation or the schematic representation which shows the synthesis of MagSeam sheets from their corresponding parent Max phases by the method called wet chemical etching method. Here actually we can see that the element A or the layer which is composed of the element A is being etched out using the HF. After the HF treatment and after sonication, we can produce MagSeams from their corresponding Max phases. It is another kind of visual representation which shows the etching out of the layer A, which is represented as that blue spheres. During the wet chemical etching method, the layer composed of this blue spheres is being etched out to produce the corresponding MagSeams. MagSeams possess very unique properties like it possesses hydrophilic surfaces. It may be mainly due to the surface functionalities like oxygen, FOH that is produced during the wet chemical etching method. It possesses high metallic conductivity in the range of 6,000 to 8,000 Siemens per centimeter, and it possesses highly negative zeta potential. It shows excellent efficient absorption of electromagnetic waves so that it can be employed for the EMI shielding applications, and it possesses high strength and moduli of elasticity. These are the applications of MAXenes. As we can see, MAXenes found several applications in the field of energy, catalysis, electronics, biomedical, environment, etc., in which we are concentrating on the energy applications of MAXenes. MAXenes are widely employed in the field of superconductors, energy storage devices like supercapacitors, ion batteries, fuel cells, and it found applications in EMI shielding and solar energy harvesting. MAXene-based supercapacitor devices possess high capacity and fast charging and discharging rates. It possesses good cyclability. It is highly lightweight and it possesses high power density and durability. The MAXene-based materials can be employed as electrodes in both electrical double-layer capacitors as well as Faraday quasi-capacitors. Here comes the importance of polymer matrix. When we are incorporating MAXene-based compounds into the polymer matrix, we are actually increasing the interlayer spacing between the MAXene sheets, which will positively contribute towards the electrochemical applications of MAXenes. MAXene-based ion batteries possess high voltage, high capacity, long cycle life, good safety performance, etc. When we are reinforcing the polymers with the MAXene, it will definitely results in the excellent flexibility, good tensile and compressive strength, and high electrical conductivity, so that MAXene-based polymer nanocomposites are widely utilized in energy storage devices, electrochemical actuators, and radio frequency shielding, etc. These are some of the examples for the various kinds of MAXene-based polymer nanocomposites, which found various applications in energy field. Here we can see that majority of the MAXenes are composed of the metal titanium. When I refer into the more literature, I can see that the one with more electrochemical performance is based on the titanium-based MAXene. It can be incorporated into polymers like polypropylene, PDDA, polyvinyl alcohol, polyacrylamide, and some natural polymers like cellulose, sodium alginate. Sodium alginate is actually a polymer which can be extracted from a seaweed. These are found applications in several kinds of energy storage devices like lithium sulfur batteries and supercapacitors. It found applications to produce or to manufacture flexible electrodes in pseudocapacitors. It found applications in EMI shielding. And as we can see, one of the other kind of MAXene, that is molybdenum-based MAXene, when it is incorporated with PE dot, it founds applications in the flexible electrodes in supercapacitors. Cellulose is another kind of polymer that is used for various kinds of energy applications. Then titanium-based MAXenes can be incorporated into PANI, that is polyaniline, P dot, PDF. Polyvinyl pyrrolidine is incorporated into MAXene quantum dots to give applications in resistive switching for non-volatile memory devices. Titanium-based MAXene with polydopamine can produce anodes for lithium-ion batteries, etc. The electrochemical characterization techniques that are generally employed for the to check the electrochemical properties of MAXene polymer nanocomposites are cyclic voltammetry, electrochemical impedance spectroscopy, and galvanostatic charge and discharge cycling. This is one of the example which shows actually the MAXene PANI composites, that is MAXene polyaniline composites, which shows tremendous electrochemical behavior when we are checking the CV, that is cyclic voltammeter, voltammogram, and the GCD curves as well as the EIS data. We can see that these materials, MAXene PANI polymer nanocomposite materials, show excellent electrochemical behavior, so that it can be widely employed in case of electrochemical devices like batteries, supercapacitors, in order to store the conventional, the green energy resources. MAXenes can be made into other hybrid materials when the MAXenes are incorporated into nanomaterials like silica, graphene, carbon nanotubes, TiO2, ZNO, and other metal oxides. Then these hybrid materials can be incorporated, or that can be dissolved, or it can be incorporated into the polymer matrix to give a much more enhanced electrochemical performance. This is one of the schematic representation route in which we are actually producing a ternary composite of vanadium-based MAXene, TiO2, and PVDF. These are my conclusions. MAXene and MAXene polymer nanocomposite act as potential candidates in energy applications. They can act as electrodes in supercapacitors. Actually, polymers act as a spacer between MAXene layers, and of course, it will increase the interlayer distances, which will positively contribute towards the electrochemical behavior of the prepared materials. MAXene polymer composites provide better specific capacitance, energy density, and current density than the parent pristine MAXene compounds. The energy applications can be validated by CV, that is cyclic voltammetry, galvanostatic charging and discharging, and the electrochemical impedance spectroscopy. These are the references.
Investigation on aluminum doped tin oxide, graphene based nanocomposites for supercapacitor applications. As we know, there is always a depletion of fossil fuels and there is a need for renewable energy storage devices. The objective of this work was to find out a alternative, that is aluminum doped tin oxide graphene composites for supercapacitor application, which has been rarely investigated. The outline of my talk includes the synthesis of aluminum doped tin oxide and its graphene composites by co-precipitation and hydrothermal method, and to analyze its physiochemical properties by XRD, FTIR, Raman, FESIM, UVDRS, and photoluminescence, and to study the specific capacitance value of the title compounds by cyclic voltammetric studies. As we know, the supercapacitors are energy storage devices and all with high capacitance value, low voltage.
Yeah, you are still on the first slide.
Sir, but I'm moving on.
Please click on the slide number on the left bar. Left column. If you click on the slides, then slide can be changed. Yes.
Okay.
Now objective slide is there, huh?
Okay,
Yes,
then
now
I
it's
will
okay.
not
Yes.
go for presentation mode.
Yes.
Is this okay, sir?
Yes, yes, please.
So there are three types of supercapacitors: EDLC, pseudocapacitor, and hybrid capacitors. The hybrid capacitors are the combination of electric AA supercapacitor with superior power density and pseudocapacitor with high energy density, combining a battery-like electrode and a pass source from capacitor-like electrode to achieve a high-performance hybrid system. The advantages of the title compounds include the energy band gap of 3.6 electron volt as catalysts and energy saving coatings and anti-static coatings in making of gas sensors, optoelectronic devices and resistors. But yet they are used in supercapacitors in cinder due to low conductivity and poor cycling property, which is enhanced by doping aluminum, which is used in the DSSC applications and the environmental pollutant degradation. Aluminum doped zinc oxide is further used as a transparent conductive oxide, which triggered me to use that compound as a dopant for enhancing the supercapacitor application work. And graphene is a world's thinnest nanoplate with a high electrical conductivity and tunable surface area, chemical stability, and mechanical behavior. So using it in a hybrid methodology and a hybrid composite, we can better get extraordinary results for different applications. So the enhanced electrochemical performance of tin oxide is expected to realize by fabricating tin oxide graphene composites. The synthesis procedure includes slight modifications in improved Hammer's method, where the sulfuric acid and orthophosphoric acid with graphite flakes are oxidized by potassium permanganate to obtain a dark brown colored solution, which is then again treated with hydrogen peroxide to obtain an yellow color solution, and then again washing it with water and 1 HCl, we get a colloidal precipitate in brown color, which is dry to get black color sheet, and they are grinded into graphite oxide powder using mortar and pestle. The synthesis of aluminum and doped tin oxide is done by using tin chloride and aluminum chloride in a co-precipitation method, where it is calcined at 600 degrees Celsius to obtain the nanoparticles, and the graphite oxide is converted to graphene oxide by ultrasonication. The sheets are exfoliated and they are mixed with the prepared nanoparticles and stirred. And in hydrothermal method, we are using 120 degrees Celsius for 3 hours for the high temperature and pressure, and they are again washed and dried to form the nanocomposites. The results of XRD are as prepared graphite oxide showed the peak intense diffraction peak at 2 theta Q theta 10.5 degree, and the XRD diffraction peaks of all the composites were matching with the JCPDS card number 411445. The strong and sharp reflection peaks of tin oxide and aluminum tin oxide composites were matching with these diffraction with this JCPDS card number, and the maximum intensity peaks 100 depicts peak broadening and lower angle shift, and the lattice parameters were calculated using d by scalar equation, and the strain was calculated using Williamson-Hall plot. The incorporation of the aluminum and its graphene composites was shown by the decrease in size of the components and the increase in strain of the material. The Fourier transform infrared spectroscopy was showing the tin oxide peaks in the range of 400 to 800 centimeters. The peak at 410 centimeters described to tin oxide or aluminum oxide box, and the peak at 560, 605 and 684 centimeter were not distinct with aluminum doping and composites. The intense absorption of the geo is seen at 1,304 centimeters. The weak absorption peak at 2352 centimeter shows the carbon dioxide present inside the compound. And the Raman spectroscopy of the tin and aluminum doped tin oxide shows the characteristics peak, shows its characteristics peak with its maximum peak at a 626 centimeter, and the as prepared geo shows the D peak at 1,352 centimeter and 1,580 centimeter. There was a peak shift to lower wave number, D peak shift to lower wave number in the composites, and the G peak shift to higher wave number, and the defect intensity ratio was high for the graphene composites of aluminum doped tin oxide. The FESM study shows that the pure tin oxide and aluminum doped tin oxide shows irregular spherical particles with less aggregation, whereas the graphene composites exhibit sheet-like morphology with multiple layers intercalated and decorated with their particles. Aggregations were seen at the surface and the edges. And the EDAX spectra further confirms the purity of the sample with the presence of tin, oxygen, aluminum chloride in the composites. The UV-DRS studies of the composites show a strong absorbance peak for all the composites in the UV region around 214 and 282 nanometer, where the graphene composites show broad absorption band in the visible range of 400 to 700 nanometer. And the band gap values were calculated using Kubelka-Munk plot, and the band gap of pure tin oxide is found to be 3.55 electron volt, and thereby the composites value got increasing with aluminum doping. The photoluminescence studies with the emission spectra in the range of 400 to 600 nanometer are shown. The violet emission of the aluminum doped tin oxide at 410 nanometer originates from the aluminum related defects, whereas the emission peaks around 550 to 600 nanometer presented by all samples are related to dangling and interstitial sites of tin oxide and aluminum doped tin oxide with the graphene sheets. The cyclic voltammetry studies were taken for all the samples in different scan rates in the potential window of minus 0.4 to plus 0.4. The specific capacitance values of all the samples were studied at the scan rate of 10 millivolt per second and was found to be 74, 333, 343 and 170 farad per gram. The CV curves of tin oxide and aluminum doped tin oxide are quasi-rectangular shape, indicating the pseudo-capacitive behavior of the prepared samples. As the scan rate increases, the specific capacitance should decrease, but there was a slight change for aluminum doped tin oxide where the specific capacitance increased. And this the scan rate increasing and the specific capacitance decreasing is due to the rapid mobility of the charges and the study. So the conclusion is the aluminum doped tin oxide particles and the composites were prepared by co-precipitation hydrothermal method. The powder XRD, FTI and Raman analysis confirms the tetragonal rutile phase structure for all synthesized samples. The removal of the functional groups from geosurface increases the degree of defect density in the composites, which were shown in the studies of UV region, ultraviolet diffuse reflected smoke spectroscopy, and photoluminescence analysis. The multicolor emission signals in the wide area confirms the presence of oxygen vacancies, and the integration of tin oxide nanoparticles on 2D graphene enhances the specific capacitance values, whereas the insertion of appropriate amount of tin oxide has to be again optimized because here we used graphene and tin oxide particles in a ratio of 50:50. But the increasing or decreasing the percentage of graphene and the metal oxide can provide a promising kind of electrode material for high performance supercapacitors. Thank you, sir.